Hi, this is Rob Bolaños. In this episode, I'm going to be talking about power distribution networks, how to do a analysis, and I will also be showing how to model. So once you have a SPICE model, you can verify your measurements against your SPICE. And once you have your SPICE model, then you can do corrective actions in case you're not meeting specs. So here are some of the items that I'm going to be touching on. I'm going to show why it is good to measure the impedance of a power distribution. Uh, as I have mentioned before in prior videos, PDN is something that has gained wide acceptance the last 5 to 10 years. It's a subject that now, because of the FPGAs, the voltage are very low, about 1.2, and the current is, or the amperage has gone way up. Now it's more critical that you have a impedance that is flat as possible across a very wide bandwidth, very high bandwidth. Okay, I'm going to show how to measure the output impedance of a VRM, which is a voltage regulator module or a power supply. I'm going to show how to model the VRM or your power supply by measuring the output impedance. And you take two measurements. You take a measurement when the power is off, and then you take it when the power is on. So these are very critical, and I'll be showing that in detail. And then I've also included, we're going to measure the impedance of the transmission line. In this case, the transmission line is a little PCB board. It's a little PCB board. It's actually an evaluation board by Picotest. And on that one, you'll be making also measurements with the input open and with the output shorted. Okay. Okay. So I'll talk a little bit of PDN. PDN is basically, it's an analysis where you calculate and you measure the output impedance of your power supply and its power distribution as a network. So in a nutshell, that's what you're doing. Okay. And what you want to do is, when you use a VNA, vector network analysis, and I'll be using the Bode100. Sorry, Bode100. Okay, so this would be the impedance. Okay, and this would be the frequency. And typically there will be a target impedance. And when you want a flat, typically you'll have the regular output impedance, and then you'll have an effective impedance where it goes up, that it looks like a inductor, and then you have your caps and so forth. Okay, so basically you want this target impedance to be at a certain level. Okay, and that level is determined by your specifications. Okay, so this is how Steve Sandler defines the target impedance, which is the voltage maximum noise and your transient uh, step that you will be setting. By the way, there is a very good application note. Here's the title of it. It's Power Distribution Network Impedance and Target Impedance. It's a paper by Steve Sandler, Eric Bogdan, and Larry Smith. I highly recommend that you look this up and explains a lot of the things that I'm mentioning here in more detail. Okay. Now, if you look at that application note, one of the things that they'll mention is that you will have some resonant frequencies, some peaks. So you may have a resonance that looks like this. So typically this represents a high impedance, especially if it's above your target. And if you hit or stimulate the network at that particular peak, well, you might have a voltage that is determined by your I peak or your I transient, and the impedance at that peak. Okay. So if this impedance is high, then your voltage peak is going to be high. Okay, and you don't want that because you might damage your device that you're powering. Okay, and we're going to go ahead and measure the output impedance, and by measuring the output impedance, it's a way of verifying your design. Okay. So in this example that I'm using with the little evaluation board that I have from Picotest, I'll be assuming a target impedance of 33 ohms. Okay, so here's a little bit of a review. This is a impedance plot of a power supply that I had measured before. This is the output impedance. But the main idea that I want to show is when you see a flat response, that's usually a resistive. Or you can think of it as a resistor. And when you have a upward slope, that's an inductor. Okay, and when you have a negative slope, that's a capacitor. And typically a capacitor will have a bottom peak and where it bottoms out, and if you have a flat response, that will be your ESR. Okay, and since it's horizontal or has a zero slope, then remember it's a resistor. And I get an outward inductance or inductor. Okay, so now that you have a intuitive of what these are the inflections supposed to mean, then we will continue. Okay, so when you use the Bode100 or any other VNA, it is important that you calibrate your unit, especially since we'll be measuring impedances around 1 milliohm. Then it's very important that you calibrate it. Now, because of the way most VNAs and the Bode100, there's a ground loop that interferes with the measurements at low frequencies, and the solution is to use a common mode transformer. In this case, I'm using the J2102B. It's a common mode transformer, and that is put in line with channel 2. Okay, so it's very important that you use a common mode transformer. And I believe if you use a VNA, I think they also have the ground loop, so I believe that the common mode transformer is a must. Okay. Another thing that would be good, or at least in my case, I am using some PDN cables from Picotest. It's these. Okay. Now the advantage that I have using these are that these are triple shielded and they have extremely low series resistance. So they're very, very good cables. So it improves the fidelity of my measurement. So if you have equivalent cables, be sure you use them. Okay. And then when you calibrate your VNA or your Bode100, you have to calibrate with open, meaning that in this case I'm using two SMA connectors connected back to back, and there's nothing in there, so it's basically an open. And once you calibrate it, then you go to the short. In this case, the center conductor is shorted to the ground conductors. And then once you have that, then you continue with the 50 ohm. In this case, I have two resistors that are 100 ohms, and they're connected in parallel, and they're connected between the center conductor and the ground. So once you have these three calibration terminals, then you can calibrate it and you should be good to go. Okay, so this is the way you connect the Bode100. Again, the channel 1 is connected, and I'm using this VRMR, which is a low regulator, and it has two SMAs that are connected right at the output of the voltage regulator. So basically these are connected to the same test point. They're measuring the same. And basically what this is called a two-port measurement. And this is the most sensitive. Okay, so this is the best measurement. Now, when you measure the voltage regulator, you're going to take two measurements. You're going to take a measurement with the power on. You'll get a Bode plot of that. And then you'll take another measurement with the power off. Okay, so when the power is on, basically you're going to measure the effective output impedance, of the power supply. And when you turn it off and you take a Bode plot, then that measures the capacitors that are on your power supply. So you need to do both measurements to extract both, and I'll show that. Okay, so another thing that I did is there's a this is the transmission line. This is connected to the voltage regulator, and this is the spot that we're measuring right here. Okay, and this is supposed to simulate, let's say, a device, or let's say a FPGA. So what we're doing is we're measuring at the end, or at the user end, or device end. Okay, in other words, we want to see what is the impedance at the device. So this is what the demonstration is all about. And again, you connect channel 1, and then channel 2 goes through uh, the common mode transformer, and this is the configuration. Again, you do 2 measurements. You're going to do a measurement with it open, and when I say open, this is what I mean. This is going to be open. In other words, you leave it alone. If you notice there's nothing in there, so basically it's not connected. And then what you do is you make another measurement with the input shorted. So basically you put a wire across the terminal to short the input. So those are the 2 measurements that you're going to do. And there's another thing, a measurement that you can do. You can do the measurement just to see what the transmission line is. And to do that, you take off the components. There's a delay on my mouse, or actually my pen. Anyway, so you remove your filters or your capacitors. That way you can characterize the transmission line, and then you can put them back on, and then make the same 2 measurements. So you'll see what I mean in a little bit. Okay, and then you connect it back together, both of them, and then you can verify, and you make a final measurement, and this is the final measurement. And the main idea is to extract a model. Or rather a SPICE model. Okay, so here is the voltage regulator, and this is where the power comes in. And this is where I connect it. And this is the first measurement that I did. And this is the Bode plot that I got. Okay, so this is with the regulator turned on. And when it's turned on, this part where it's flat, this is the output impedance of the VR amp or the voltage regulator. Okay, so it's typically very, very low. In this case, it's 16.2. And to model that, then you can put a resistor like so. Okay, and then if you notice right here, there's a low inflection point. Right there it starts. And remember, I mentioned anytime there's a little bit of inflection, then you can assume that there's a inductor. So there's an effective inductance of the VMR, and by measuring the impedance, you can calculate the inductance of your regulator. So in this case, I calculated that it was 56 nanohenries. So then I can put that here. Okay. And then there's a downward inflection, and typically this would be the capacitor. Okay. This is inflection, and since it looks like it bottoms down, so this inflection is a cap, and then right there where it has 0 slope, that's the ESR. And typically this will be the ESL, of the cap. Okay. So for now, these two actually show up here when you measure or you take another Bode plug in the off. So for right now, these two parameters are taken when the regulator is turned on. Okay. Okay, so now with it turned off, then you'll see that you have a 1 ohm impedance, a very low frequency, and then you have a cap. This is the cap that's inside. It's going to be this one. And then here is the ESR of the cap. And then here is the ESL. So here are my values. Here's my cap. Here is the ESR. And then here is my ESL. Okay. And then this one, this is 1 ohm. Okay, it's not 10, it's 1 ohm. And that is modeled by that. So now this is the voltage regulator model. This is your SPICE model. Okay, so now we're going to model, or we're going to measure the pico test, the coupling, or rather the transmission line. There's a line that goes underneath. And in this one, well, what I did, if you notice, it says bare transmission line shorted, bare transmission line open. So basically what I did is, when I say bare, it means that the components are taken off. So I remove basically a resistor and a cap. Those are the only two components. So I removed them and I take a measurement. And why? Because I want to characterize the transmission line. So here are the two measurements. From here I can see that when I short the input, and if you notice right here, I have a wire that is shorting the input. Basically I'm shorting this line to that line. I'm shorting the input, and I'm measuring right here at these 2 points. These are where the SMAs are. Okay, so with that being said, then I measured that it has the transmission has a 5.5 ohm resistance, and then here, that is the inductance, and that is modeled by a series inductor. And then when I open it, in other words, I remove the short, I remove the short, then I measure the capacitance, and the capacitance turns out to be 70 picofarads, which is right there. Okay, so now I went ahead and put the capacitors back on, put parts back on. Okay, so basically I put the resistor and the cap. Okay, so now I do a same measurement. So now I'm going to short it. Here's the short. Okay, and if you notice, I'm reading the same resistance. That's the transmission line that I'm reading. And then I have this has a little bit of inflection, and if you measure the impedance, I calculated 8.1. And remember, I already, knowing that this is shorted, that 8 is including the 6 already. Okay, so that means there's another inductance. So the difference is this inductor. So the 6 plus the 2 will give you the 8. Okay, and then there's a little, this is the capacitor's ESR, and then this is the cap's ESL. Okay, now this ESL should be this one as well. Okay, so in the model, I'm going to choose the bigger number. So it's probably a little bit of a measurement error or some interaction that I'm not accounting for. But for my model, I'm going to use the largest number. So since this is the ESL, both measurements are the ESL measurement of the capacitor. Okay, so this is a shorted. Now this is the open one. So basically I removed that. And now I'm measuring the characteristics of the capacitor and the resistor that's in my circuit. So by measuring that, I can tell that it's a 10.75 microfarad cap, or microfarad cap, and then it has approximately 30 milliohms. That's because of the resistor. The resistor is actually at 33, so I went ahead and put 30 milliohms. And then, like I mentioned, I am using the highest ESL of the two, and I use the 1.81 nanohenries. Okay, so now I have that. So now I have my complete model. So I have the model that I've already extracted with the Bode100. Now I have the model for the T line, and now I have the model for my bypass capacitor has been modeled. And when I measure, this is the impedance plot that my device would see. And if you notice, this is 10, 20, 30, so it's about 33, actually 33 milliohms. And you can say that it's approximately maybe a 2 megahertz bandwidth. Okay, once you go above that, then you're exceeding the 33 milliohm target impedance that I've set. So this is 10, 20, so the target would be around right there. T8 target. Okay. Okay, so now we're going to simulate it. And when I do the simulation of my circuit that I just extracted, if you'll notice, it's almost a match. It looks almost exactly the same. If you notice, this is what 20, 25, somewhere around there. This is 10, 20. So this is pretty good. And then you notice there's two humps. I got the two humps here. Okay, and then if you notice, I have basically almost the same bandwidth. And then look at this point right here. This is 10 megahertz, I have an impedance of 100 milliohms, and it just so happens that 100 milliohms, and at 10, basically the same impedance. I have 100 milliohms. Okay, so this tells you that the model is a match. So now you can use the model to improve your situation. Okay, so let me go back here. Okay, so what can we do to improve the impedance? The goal is to bring this out a little further, out like this, as far out as you can. And knowing that this impedance is 1.59, and this is the effective, this is the measurement or the formula to calculate what the inductance is. Once you know the inductance, then you can use this formula. So basically, it's the L effective divided by the target impedance squared. So in this case, it's 1.59 millihenries or nanohenries divided by 33 milliohms squared. So we need a capacitor of 1.46 microfarads. Okay. So what I did is, these are 1 microfarad each, and I downloaded the spice from Kemet, and when I insert them into my model, if you notice now, this is the original. Okay, and now this is the new. Okay, and if you notice right here, at the bandwidth of about 13, I'm at 33 milliohms. Okay, so now we have this little deep dip. So this is the capacitor. These are the two 1 microfarad that I added, and then this is the ESL of the 2 microfarads that I added. Now, if you want to make this flat, then you can add ESR resistors if you can find values that low. And here's the example. So basically, I need 33. So in Spice, it's easy to add resistors. So I add 266. So that's 33. And if you notice now, remember it had the little dip. Now it's eliminated, and we still keep, well, basically it did reduce it a little bit, but you do have a increase in bandwidth. Okay, so now you can calculate what the inductance is of this spot, and you can keep doing this until you add more capacitors until you bring it up higher and higher. So you keep repeating and add more caps until you achieve the flat target impedance that you need. So in a nutshell, that's what PDN is. It's a good way of verifying your design using the Bode100 or any VNA. You can take these measurements, and once you extract your model, then you can use Spice to improve and make that impedance as flat as possible. Okay, so hopefully uh, you'll find this video useful. If you find it useful, please subscribe, give it a thumbs up, and share. Thank you for your attention.